the questions that we have to answer to describe this oscillatory motion is, what is the minimum energy to start the oscillation? The second question that we have to answer is so the second question we have to answer is the first question even before that is whether the motion is going to start, right. So, what is the condition for the starting of the oscillatory motion, and then the second question is what is the minimum energy that is required to start the motion of the oscillatory nanotube, and finally, how can we describe the motion of these oscillatory nanotubes. So, I am going to describe this model first by standard Newtonian mechanics, and then later on I am going to describe the same model using our variational calculus and to come up at the same result that we began with. Okay. So, we are going to start our description of the model of the oscillatory nanotube. So, modeling nanotube inside nanotube oscillator. Okay. And the nanotube oscillator, let me just draw two nanotubes, and I see that the inner nanotube is the following, right. So, this is at a distance d, and this will be drawn outside and then also drawn inside. So, in this device what we have is a double walled, we call this as a double walled nanotube oscillator, and it starts when we pull the inner nanotube by a certain distance, let us say d, right. And then we are going to assume in this motion that this pulling is not that much that the inner nanotube completely comes out of the outer nanotube, or we are assuming that there are no edge effects of the outer nanotube with the inner nanotube. Otherwise, if the entire inner nanotube gets pulled out, we will see that we expect that the motion is going to stop and the model is going to fail. Okay. So, in this device, a double walled carbon nanotube starts with its inner tube extruded by a distance d, right, out of fixed open ended outer carbon nanotube. Okay. Okay. So, which means that the moment we pull out the inner nanotube, we expect that the van der Waal interaction energy or the van der Waal force that is generated due to this pulling out effect is going to suck the inner nanotube back into the outer nanotube. However, due to inertia, the motion will continue inside the outer nanotube, and the inner nanotube will go partially out from the other end, and then due to inertia the motion is going to again repeat and we will get a cycle or the oscillatory cycle. Okay. So, what I said is the following. So, my excess van der Waal force sucks the inner nanotube back, right, and I see that there is a reversal of the direction at the opposite end, right, of the outer nanotube, because of the inertia itself, which returns the oscillatory inner nanotubes back to its starting location, which which returns the oscillatory inner tube back to its starting location. Okay. So, that is the motion that we are going to try to model. Okay. So, then as I said, we have to answer 3 questions. Let me write down those questions. So, the first question that is to be answered is, will the inner nanotube be sucked into outer nanotube. Okay. And we call this as my acceptance criteria, acceptance condition. And the second question is, how much energy is picked up, picked up by the oscillating nanotube, And the third question that we want to answer is, how can we quantify this oscillatory motion, or for example, what is the oscillatory time period or the oscillatory frequency of this motion. So, what will be the oscillatory frequency of this motion. Okay. So, the assumption is the 2 nanotubes interact, so that the interact completely via the inner portion of the nested inner nanotube. Okay. So, which means that the outer portion, so again let us go back to the diagram, the outer portion of the inner nanotube does not contribute to the interaction energy of the motion of these nanotubes. Okay. Okay. So, what I have is, the assumption before I answer this question is, assume the 2 nanotubes only interact along the inner portion, only interact along the inner portion of the nested inner tube, right, or it is equivalent to saying that the extruded portion of the inner tube does not contribute. Okay. Okay. So, the extruded portion does not contribute, fine. So, let us start answering all those questions. So, the first question is the acceptance criteria, will the nanotube be sucked into the outer one, and the answer is yes, as long as the interaction energy is negative or attractive, right. So, consider the answer to this question is, we need to consider the sign of the interaction energy. So, consider ECC. Notice that we have evaluated the interaction of these 2 nanotubes. Notice we call this cylinder interaction as ECC. We find that it is equal to the following expression. The ECC expression is this one here, which is a boxed expression. So, we will be using these expressions in the L format. So, as long as ECC is negative, we expect that the inner tube will be sucked into the outer tube. So, my ECC, let me call this as the starred value, this is 3 pi eta c whole square B 1 divided by 4 B 2 to the power 4 times minus A of L 5 plus 21 by 32 B by B 2 to the power 6 of L 11, right. We see that if I have, if E C C star is greater than 0, then the net interaction energy is repulsive and the inner nanotube will be pushed out of the outer nanotube. So, we will not have the oscillatory motion. Okay. So, the net interaction is repulsive, and we see that the inner tube will be pushed out of the outer tube. Okay. Fine. So, that answer the acceptance criteria. The second question is, what is the suction energy, right. So, the moment we ascertain the sign of the interaction energy, which needs to be negative, the suction energy is equal to the work done on the system initially, right. So, my suction energy is, so if I provided my interaction energy is, the cylinder interaction energy is negative, then my, let me call this as SE, then my suction energy is work done in extruding the cylinder out of the outer cylinder. So, again my cylinder is as follows. I see that the inner cylinder has been extruded initially by a distance d. So, my suction energy will be equal to the work done, which is also equal to negative E C C star times d. Note that I have put a minus sign, so that I can get a positive work done. Okay. So, this is the work done in extruding out the inner cylinder, the inner cylinder by a distance d. Okay. Okay. So, that answers what is the suction energy which will drive the system. The third and the most vital question is describing the mechanics of the setup. Okay. So, then to answer the to describe the oscillatory motion of the two nanotubes, let us look at these two tubes of a certain length, which are in which the initial tube is extruded by a distance d. So, let us say that in general I have the outer tube, let us say it is of length L 2, and let me also show that the inner tube is at a distance, well, it is of length L 1, right, and they are all coaxial. So, that is the assumption, and let us say that the center of L 1, well, let me call this distance as, for convenience I am going to call this distance as 2 L 2 and this distance as 2 L 1. Okay. So, we see that for convenience I have the center of all the axis is the origin, right, and the center of the inner cylinder is at a distance z comma 0, right. So, the setup is as following. So, to look at the oscillatory dynamics, let us assume inner and outer nanotube of length 2 L 1 to L 2, right, and we also assume the center, we assume that the center of the outer nanotube, is at the origin, is at 0 comma 0. So, the outer nanotube of length 2 L, while the center of the inner nanotube is at at initial point z comma 0. So, it is slightly shifted. So, z is going to be our distance from the center through which we are going to describe the oscillatory motion, right. So, we expect that at equilibrium z is 0, otherwise in the oscillatory motion z changes its value. Okay. So, then further what we have is that the ends of so which means that the ends of, so these are all my assumptions. Also assume that the ends of my outer or inner cylinder, right. Notice that outer cylinder is of length 2L. So, the ends of the outer cylinder or the inner or the outer nanotube is at length plus minus L2, and my inner cylinder is of length z plus minus L1, right. My outer cylinder is of length L2 and my inner cylinder is of length z plus minus L1. Okay. And then in my oscillatory motion we will see that we have 5 different cases where the center of the inner cylinder can remain with respect to the origin. So, I am going to describe the motion in 5 different stages. So, or let me call this is in the form of 5 cases. So, my case 1 is when the center of the inner cylinder is extremely far apart, or when my z is less than minus L1 plus L2. So, it is outside the outer cylinder, right, and outer cylinder, so that there is no edge effects as well. So, which means that the inner tube in this case is fully extruded, inner tube is fully extruded along negative z axis. Inner tube is fully extruded along the negative z axis, and then in case 2 I have that z varies from, it can vary from minus L1 plus L2. So, it is certainly inside, partially inside, to minus L2 minus L1, right, or let me call this as L1 minus L2, right. So, this is indeed in partially inside, but well L2 is bigger than L1. So, let me put it write it like this. So, minus of L2 minus L1. So, Z is partially inside, the inner tube is partially inside the outer tube, but still in the positive along the negative z axis, along the negative axial direction, right. So, in this case we have the inner tube partially extruded along negative z axis. The inner tube is partially extruded along the negative z axis. Then my third case is when it is completely inside the outer tube. So, suppose I have that z is between L1 minus L2 to L2 minus L1, right. So, let me write it in the minus form. So, L2 minus L1 with a minus sign, and then it is with a plus sign. So, here I have the inner tube is fully inside the outer tube, right. So, these are my various positions of the center of the inner tube. Then I could also have that the inner tube is partially contained inside the outer tube, but along the positive z axis. So, which means that z is from L2 minus L1 to L2 plus L1, and then this is where the inner tube is partially extruded, in the positive z axis. Okay. And then fifth case is I have that z is bigger than L 2 plus L 1, and this is the case where the inner tube is fully extruded out of the outer tube, but in the positive z direction. So, inner tube fully extruded along positive z axis, right. And to describe the oscillatory motions, these 5 cases are repeated twice, right. So, these 5 cases are going to be repeated once for half the motion of the nanotube, okay, or half the time period of the nanotube. Okay. So, then the next stage is to describe these stages of motion using the interaction energy. So, note that in case 1 and case 5 there is absolutely no interaction. So, we can assume that in 1 and 5 there is the interaction energy is 0. So, assume before we do that, note that these 5 cases involve 4 boundaries. One boundary is this point, the other boundary this point, the third boundary this point, and the fourth boundary this point. So, my cutoff points or my boundary points are given by z is equal to plus minus L 1 plus minus L 2. So, there are 4 cutoff points. Okay. So, that is the point we will note. So, then notice that we are going to assume that in case 5 and case 1 the interaction energy is 0, because there is no interaction with our assumption. So, assume fully extruded state, fully extruded states 1 and 5 gives ECC equal to 0, right. And for other states the work done increases by ECC star times the length or the distance that the nanotube travels, right. For other states, W increases by ECC star times the interaction length, Okay. Okay. We see that in this case W will be in case. So, we have 3 more cases left. So, in case 2 W will be ECC star times L 1 plus L 2 plus Z, right. And in my case 4, so case 2 and case 4 are very similar, one in the negative z axis, the other in the positive. I see that this is ECC star times L 1 plus L 2 minus z, and finally, in state 3 or case 3 where the tube is completely inside, I see that the work done is ECC star times the length of the inner tube, which is 2 L 1, times the length of the inner tube, which is 2 L 1. And what I have is the following. So, what ECC star now is negative by its definition, because it is a suction interaction energy, the attractive interaction energy. So, what I have written down is negative of the work done, right. So, if I were to plot this negative W, on with respect to Z, I will see that we have the following 5 stages. So, this is my Z axis. So, let me now break down into following 5 stages. I have 3, I have 4, so I have 3 and 4, stage number 3, stage number 4 and stage number 2 and stage number 1, stage number 1 and stage number 5. Okay. So, I have divided into 5 different stages. So, let me remove all these arrows, because the diagram becomes little clearer. So, this is my negative w axis, okay, and I see that I get the following curve. So, this times this and this. Okay. So, this is my stage 3, these are my stage 2 and my stage 4 and my stage 1 and 5 are given by this. So, we can see that in stage 1 and 5 the work done is 0, and in stage 2 the work done is decreasing with z, and in stage in stage 4 the work done is increasing with z, right. In stage 3 or in case 3 the work done is constant. We can see that it is independent of z, which is given by ECC times 2 L1. Okay. So, the diagram here is important, because we can see that there is 0 acceleration of the particle or the nanotube at for case 1, case 3 and case 5. The only acceleration is or / deceleration is in case 2 and 4, right.